Here's my lab report for Lab 9 Part 1. The problem that I had to deal with was analyzing a spring motion similar to the extreme rope sports video that Dr. Schatz and Dr. Greco showed us in lab. They presented us with a video in which we had to analyze. I plotted the X and Y positions of this mass for every frame of the video. And the frames per second of the video was one frame for 10.5 frames per second. And then I calibrated the distance of everything by using the equilibrium length of this spring and mass, which was 0.7 meters. And here are my X and Y positions for time over here, and here are the two graphs. Before I go into showing you the model, I use these equations to find some values for my model. I use the oscillation period, how long it takes for a period to oscillate, which is equal to 2 pi over k over m to the 1/2. I knew everything but k, which is a spring constant, and I solved for that. With that spring constant, I could solve for the change in length of the spring, and from that I could find the relaxed length of the spring. In my model, you'll see that I use force of gravity, the force of spring, and the force F net force. And the force of gravity is mass times the g constant, force of spring is the spring constant times the change in length, and the net force is both of them added together. And to find the position of my mass in the model, I use derivations of the momentum principle, which is dp dt equals F net. Then I also used the potential gravitational energy, which is this 1/2 k times s squared, and then the kinetic energy, which is 1/2 mv squared, and the potential energy, which is mass times the g constant times height. And then the change of each is the final minus initial. So here's my model. The attachment point is at 0, 0, 0. The mass is 0.402 kilograms, which is what was mentioned in the video, And then I have the initial ball position as the same position as the position in tracker. And then I saved all these values into a CVS file, which I loaded into my model to show the position of the tracker while showing the position of my model. Plugged in the KS, the relaxed length, and then you can see this is where I put the equations into my model, and here's the momentum principle being used to update position. And here's how I defined all my change in energies. In the plot, I'll be plotting all of the delta energies. And here's my model. The blue ball is the tracker video positions, and the yellow ball is my the model positions. And here are the potential energies. The blue and the red are the potential and kinetic energies, change in potential and kinetic energies. And the green is the change in the spring potential energy. And from these, I was able to plot the X components of the model and the experiment, and they seem very accurate. The model predicted the experiment very accurately, and same with the Y component. And from these, I was able to get the oscillation periods of the X and Y, which I'll use later in my discussion. And then here is my change in spring potential energy, which I was able to plot also. So compare the x and y components and their oscillation periods. The x had a shorter oscillation period by 0.1 seconds, which makes sense because the x component had a bigger displacement, so it oscillated faster than the y component. And then the second question deals with the system. The system before was the mass plus earth, and the system afterwards was the mass plus earth plus spring. Since there was no work done by the surroundings in the system afterwards, the energy principle would equal 0 right here. No work. We're going to ignore Q for now. So change of energy would equal to 0. And that's why we added the spring potential energy into the problem, and that satisfied the energy principle. And then the third question asks us what would happen if we changed the location of the initial spring position. So if we put the initial spring position right here at the equilibrium length of the spring and ball system. So the equilibrium length was negative 0.7, and then we'll see what happens. The y position was changed. Y positions changed. They're basically amplified, while the x positions did not change. And you can see that this change amplified everything in my plots. Okay, that's my video. Thanks for watching.